I've known him since his beard was this high, so known him a long time. He's going to be talking about Pledge, so let's give it up for Rob Keizer.
Thank you, thank you. Yeah, I'll wander that way. Sorry to the sound guy. So I'm going to be talking about Pledge. I've got 14 slides, I think, in total. It's not going to take that long. It is an introduction. I'm sorry to all of you who actually know what I'm talking about. Some of you won't, which is what, yeah, people should be using this. So very simple. I'm Rob Keizer. I'm speaking as myself, and this is an introduction to Pledge. So I work at a bunch of different organizations, and this is me. Feel free to interrupt at any point. I'm not picky about it. So we're going to be covering what Pledge is and why does it exist is more to the point. There's a bunch of different solutions that do the same thing in different ways. So if you don't know about AppSec, we'll go over it, but AppSec, SE Linux, SecComp, those kind of things, that's the whole point of it. This existed before. I'm going to go over the recent history and why I'm talking about it and the basic usage of Pledge. And that's it. I kid you not. This is going to be a very quick talk. So really simply, why does it exist? Programs exist. Well-designed programs are a smaller subset of that. And secure programs are a smaller subset of that. And at the end of all things, programs do a bunch of stuff. A computer really isn't all that useful if it doesn't have some programs or some code that it runs on. And most of the security issues, unless you're talking about really shitty firmware, which is by itself a program, generally speaking, that's where your security problem is going to be, right? And the one thing that I want to make a point of here is that there's two different mechanisms to do this. There's a bunch of different implementation details, but one way that's traditionally happened in the last 20 years of computer security is you set up an operating system or you set up some system to put controls and bounds on your program. You say, okay, I'm going to apply these things, and when you cross this line, I'm just going to do something. There's another way to do this, which is programs know what they should be doing. And so if you empower the computer program to self-limit, to say, hey, if I do this or anything other than these things, I've gone wrong, I've gone bad, I've been hacked somehow, there's a problem with configuration. So there's a big distinction there, and it has to do with how you come about the problem, whether or not you're solving for an operating system applying things, or whether or not you're saying a computer program being able to self-identify as this is what I'm going to do. I'm just out of curiosity, if I say SE Linux, most people are going to raise their hand, I'm assuming. Familiar with the concept? Yeah, good. SecComp? Yes? Half the room? Okay, good. It's going to be nice and quick. So operating systems provide system calls. So if you're a program, you want to open a network port, you have to talk to the kernel somehow. Different implementations of operating systems will have different mechanisms for this, but you have to talk to the kernel somehow to do the thing. And so that's not really an accurate statement. Why not limit the system calls? It is in some ways. There are different mechanisms for it. But basically what we're talking about is when a computer program goes and does something talking to the kernel, there's a permission boundary check there that's inherent. So operating systems will use processes or different users. We had all kinds of people talking about different, exposing it through the entire stack that is the goddamn awful shit of containers. I say that running the archives production Nomad cluster. So anyways, so if this seems familiar, it's because it is. Oh, that's horrible. So I'm going to just go over it. So AppArmor came out in '98 for Linux. SE Linux came out in 2000. It's ACL based and in the kernel. SecComp came out in 2005. It's again in the Linux kernel. And I'll go over what these are very briefly. Capsicum is FreeBSD's version of the same but different, is the simple way to look at that. The people who are into FreeBSD will probably know what the differences are. It is slightly different, slightly variant, but at the end of the day, it is the same shit, different pile. And Pledge, which is what this talk is about, and it's OpenBSD's version of the same thing. Again, I'm making overly generalized statements. It's not exactly true, but it's true enough that you can have a conversation in a pub, and it'll be accurate. It's worth noting, AppArmor and SE Linux they use what's called the Linux security modules. Basically, you can think of that as a bunch of hooks. So I'm going to get this wrong because I know for a fact there are people in this room who have actually hacked on this code and actually exploited these systems. But as a generalized statement, the systems over there were designed so that when you talk to the kernel basically checks whether or not this program is allowed to touch this object or this thing that exists in the kernel. And that's different from other mechanisms of doing the same thing. Like the end goal is to say, hey, I'm a program, I should only do this thing. How that actually happens changes. So operating systems, setcomp is the standard, setcomp BPF, which is ironically, I think it's still Berkeley packet filter, and it comes out of that, and then, yeah. Anyways, like I said, 13 slides, 14 slides. This is going to go quick. So LSMs versus setcomp, very simply, this is not an accurate thing, but it's close enough. When a user program actually asks to do something, you can either have it be specific to individual resources within the kernel, basically, or you can try and limit it when it talks to the kernel, where it says, if you talk to me, if you talk to the kernel in this way, you can't, go away, or you get killed, or similar. Versus, I can talk to whatever I want, and then I'm going to do something when that happens. So those are the two different models. The hierarchical kernel objects, setcomp basically is a one-way gate. It's a one-way street. It is very analogous to pledge in some ways. It basically allows the computer program to say, hey, I will not do these things. If I do these things, kill me. Yeah, there you go. And this is, again, not entirely correct, but it's close enough. So operating systems apply LSMs, and apps use setcomp. It's accurate-ish. It's not perfect, but it's close enough. But this basically represents the two mechanisms of solving the same problem. Either you have an operating system, which is configured with SE Linux, or your other implementation of LSM, or your policies, or your AppArmor systems, or your GRSec security kernel systems, or whatever. Basically, you either have a system designed to limit applications, or you have an application that says, I'm going to do these things. And just to be very clear, you should use both of these things at the same time. So back to pledge. It's native to OpenBSD. It is very similar to setcomp. That's what it looks like as an interface. So it's just a single call. You pass it a string, two strings technically, one of pledges, which we'll get into what that is, and one with promises, and one's exec promises. They're the exact same thing, but one of which applies to children or descendants of. And they are basically groups of things you can do. So we'll get into it very, very quickly. Setcomp BPF requires you to understand things a lot more than this level of abstraction. The whole point of this is that it makes it easy for programmers who might actually want to implement some kind of reasonable security. A good example of this is, say, grep or cat, or take your pick of utility that is not going to talk to the network. There's absolutely no reason the grep binary needs to open a goddamn port. If it does, it should probably be killed. Wouldn't it be nice if grep said, I will only talk to the file handles that are standard in, standard out, that kind of stuff? That's where this comes in. You can see that there's stdio, rpath, like read, write, inet, process, all that stuff. It's basically just saying you've got a whole bunch of system calls that are what the operating system provides as an interface to do stuff. You're grouping them together into things that programs are going to use naturally together. The only difference, well, the main difference between promises and exec promises is that exec promises are inherited by children. So again, this is a one-way street. You basically say, I am going to do this thing, and if I fork, if I create a child process, if I do anything, it's still going to apply if it's in exec promises. The big thing that I wanted to talk about this is recently it was polyfilled, so pledge. This is talking about pledge. Recently it was polyfilled into Linux in 2022, and they did a pledge to setcomp BPF translation layer, which means that all of us now don't have to deal with setcomp BPF as much. I mean, we do, and there are people in the room who will care a lot, but that is a huge barrier to entry, and you'll see why in a second. Also, I run Nomad these days. HashiCorp has a Nomad community driver that is like pledge. So in places where you would normally have a shell script where you're like, I'm going to do this thing, whether it's deployed through Ansible or Nomad or take your pick, you probably don't want your random shell script. Like if you're going to fucking do it and do straight up like curl pipe to bash, at least make sure that the binary in the middle has this protection so that it will do what it's supposed to do and not do other things. So, like I said, actually usable translation from promises to BPF. And this is important because that's what that does. As a programmer, you're not writing that. It's just not going to happen. You're not going to get adoption. Theoretically, and just to be fair, this is one implementation of, and it's not entirely accurate, but it's close enough, and it was the example that was used. You need to make this stuff available to people. We got a whole bunch of people who are not security experts writing code. We should give them the tools to write code that can self-limit. So this is an abstraction layer that allows you to do that as a programmer in a real way and not have to worry about all the details on the implementation side. I've got, I think, 4 slides about, hey, this is how you can use it in that language, and we're done. So it is nice and quick. So with Rust, you can, and so there's a thing on here called Unveil. I'm not going to go into Unveil, but it goes hand in hand, and it's basically the same idea, but with file systems and CH roots. Very broadly speaking. It's not entirely correct. There are distinctions there. People will get upset if I say things that are not incorrect, but it's generally true. So with Rust, you literally just use the crate, and you're done. With Node, there's a package for it. You just use it. With Elixir, there's just a package. You just use it. With Python, you can use the C interface, where you use the same thing. My point is that this is available in languages and programming languages that you actually use. So please use it. That's it. Questions, comments, concerns, heckles? Yeah.
Have you seen a lot of adoption outside of the OpenBSD world so far?
Yeah, so I mentioned the Linux Polyfill earlier. There's been a couple different things. So the question was, have I seen adoption outside of the OpenBSD world? The answer is yes, because what people are doing with this translation layer, where Linux has BPF and a few other seccomp things, this translation layer allows you to target sane things and have it apply across different operating systems. So with this polyfill, with this translation layer, I'm seeing it actually being used properly in Linux binaries, which is something that we weren't seeing people use proper seccomp BPF filters in Linux binaries. Now we are by way of this. Yes, it's a translation layer. Yes, it's not ideal, but they're using something. So, yeah. Cool. Come talk to me about reconfigurable computing or, the archive or this stuff. Anyways, Ron.